Good day, class, and we are going to be having chemistry. The topic we are talking about is elements and their symbols. And from the periodic table, we can see all the elements that we have. Presently, we have about 118 elements in the periodic table. However, we are going to be seeing the names of the first 30 elements. Now, this is a simple process. There was this particular scientist called Berzelius who suggested how to give elements their symbols using some simple designs. And this man gave us just 4 cases where we can arrange elements based on their symbol. And we are going to be seeing that right away. Before that, we need to write the names, the symbols of these first 30 elements from hydrogen to zinc. Let's see. Hydrogen is H. Helium is He. Lithium is Li. Beryllium is Be. Boron is B. Carbon C. Nitrogen N. Oxygen O. Fluorine F. Neon Ne. Sodium Na. Magnesium Mg. Aluminium Al. What about silicon? Sr. Phosphorus P. Sulfur S. Chlorine Cl. Argon Ar. What about potassium K. Calcium Ca. And the next is scandium Sc. Titanium Ti. Vanadium is symbolized V. Chromium Cr. Manganese Mn. Iron Fe. Cobalt Co. Nickel Ni. Copper Cu. Zinc Z. And what do we discover here? We notice that no two elements have the same symbol, meaning that every element has its unique symbol. There is no element that has the same symbol with another element in the periodic table. So, how are we going to segregate this? How are we going to know which is in case 1 or case 2 or 3 or 4 according to Berzelius? Calm down. All we have to go for is case 1. The man suggested that for case 1, we pick only the first letter of that element's name, and it has to be a capital letter. So, elements with first letter only. Element with first letter only. So, let's see from 1 to 30, what are the elements that have just their first letter as their symbol? Hydrogen is a nice example. So we have hydrogen, and that symbolized H, just the first letter, like your initial. So which other one do we have? We have boron. Boron is also a family of this. Carbon is also a family of case 1, carbon. As well, we have nitrogen. Nitrogen. So the condition is, for case 1, we pick the elements that have their symbol, just the first letter of their element's name. So we can still see more of that. Let's figure out. Yes, we have oxygen, just the first letter. Fluorine. We have, which other one? Phosphorus. Likewise, sulfur, just the first letter. And this is the only letter, look at it, P, but here is K. So that is not going to be in case 1. Let's figure out more. We have vanadium, and that is the list of elements in case 1. We are picking the first 30 elements. You can figure out on the periodic table right on your screen to see which other elements are right in case 1. Let's see, case 2. What did this man say about case 2? Case 2. He said that elements with first and immediate second letters. Elements with the first letter and the second letter that follows after it. Let's figure out those elements to know which elements belong to case 2. And we have helium. The first letter and the second letter just right in case 2. Helium. Which other elements? Lithium. Li. The first and the second that follows immediately. Lithium. The next is beryllium. B and E. Beryllium. It's a very nice example. So let's figure out which other elements will fall in case 2. Let's see. Lithium as mentioned, beryllium as mentioned, neon will also fall in case 2. But check out sodium. It doesn't start with the same letter, neither is the second letter the same. So it's never going to be in case 2. Let's see, aluminium. First and second. Silicon. Nice example. Chlorine will never be, because chlorine is having C, but the next letter is H here, whereas we have L. So it's not going to be in case 2. Argon is a very nice example. Calcium is a nice example under case 2. Scandium, titanium, which other one? Cobalt, good. Nickel, good. And that's all. Now, this man said we still have some other element that we have not grouped into any of these 2 cases. He then said case 3 will be case 3. Elements with first letter and any other letter. So this is case 3. Elements with the first letter and any other letter which must not be the second letter. So the first letter and maybe the third, the fourth, or any other one that is attached to that name of that element. So let's figure out what the element could be. Of course, we have magnesium, the first letter, and any other one which is not the second, and that is in case 3, magnesium. Also, we have chlorine. Chlorine. Likewise, we have which other one? Chromium. Chromium. We also have manganese. Which other one do we have here? Copper is not, because the first letter, any other one which is not the second, there is no U here, so it's not. Zinc is also going to be in case 3. If you watch well, you discover that we have not marked some elements, which means we have not given their position in any of these 3 cases. Then this man suggested the last case, case 4. Elements with their Latin names. Now, the remaining elements that do not fall into any of these first 3 cases is going to fall in case 4. Elements that have their Latin names with them. So let's see, we have which example right here. Okay, we can see sodium. Sodium, this Na is natrium. Natrium, Natrium. It's a Latin name for sodium. So sodium falls in case 4. Sodium. And potassium. Potassium falls in case 4. Letter K. Potassium. Let's figure out which other one do we have. So we have iron. Iron. Iron is ferrium. Ferrium. Fe for iron, which is ferrium. And which other one? Copper. Copper is cuprium, from the Latin name cuprium. So this is the list of the elements, how they can be grouped, how they can be symbolized, how we can categorize them into their different cases. And of course, we still have many other elements in the periodic table which you can figure out which case remaining elements belong to. And I hope this is clear to us that we have 4 cases according to Berzelius. The case 1 is element with their first letter only. Case 2 is element with the first letter and their second letter, which follows immediately. The next is case 3, elements with the first letter and any other letter in the name of that element. And case 4 is elements with their Latin names. Come back to class, and we are going to be talking about the valence electrons of elements. The valence electrons of elements. What do we mean by valence electron? Valence electron is the number of electrons in the outermost shell of an element. Are you confused about shell? Don't worry. All you have to do is calm down. Now, for us to understand how electrons are arranged in a shell, we need to understand this principle we are having on the board. The shell is just the region where electrons can be arranged. So we are having the first shell, it's usually called K shell. And we have the L shell, which is the second shell. And the third shell is the M shell. Supposing we have another shell, we call it N shell. How then do we know how many electrons will fall in each of these shells that we have given? You don't need to panic. The simple logic is using the formula 2 into bracket n power 2, where this n is the number of shell and it is never equal to 0. So in the innermost portion here is actually where you have the proton and the neutron of an atom. However, we will not be focusing on that since we are not talking about the innermost part of the atom. So let's see, how do we know the maximum number of electrons for K shell? How many electrons will be present in the K shell? It's very simple. K is the first shell, and that is our n equals to 1. Using the formula, we figure out 2 into 1 and power 2, where my 1 is the number of shell, the position of the shell. 1 power 2 is 1, and we have 2 into 1. 2 times 1, which is 2 electrons. That is to tell us that the highest number of electrons that K will occupy is just 2. So we have 2 electrons right there. Let's see, what will be the maximum number of electrons for the L shell? Remember that L is position 2. So my n for L shell, n is 2. And using the formula again, I have 2 brackets n squared, where my n is now 2. So I put 2 here. 2 power 2 is 4. And that's 2 in 4, which is 8. So my shell L will contain 8 electrons. So that means the maximum number of electrons that this L can occupy is 8 electrons. And now let's see the next shell, which is M shell. How many electrons can be occupied in the M shell? We have our number of the position of L is 1, 2, 3. M is on position 3. So that's my N, which is 3. Using the formula again, I have 3 power 2, which is 9. So I have 2 into 9. And the number of electron in M shell is 2 times 9, 18 electrons. So that is the maximum number of electron M can occupy, and that is 18 electron. You can configure the next, which is N, to figure out how many electrons were present in the N shell. So don't forget, we are still talking about the valence electron. Now let's figure out how many electrons will be present on the outermost shell of each of these elements that we have written. As we have already listed the numbers beside it, the numbers are indicating the number of electrons present in each of the elements. So if I would ask you, how many electrons does aluminium have? Trace that, 13. Aluminium has 13 electrons. If I would ask you again, how many electrons does oxygen have? And oxygen has 8 electrons. If I would ask you again, how many electrons does calcium have? A calcium atom has 20 electrons. Now, let us figure out the configuration of these elements using the shell principle. Good. For hydrogen is having 1 electron, and the first shell, which is K, will occupy just 1 electron. So, the valence electron of hydrogen is 2. Valence electron is 2. The valence electron of hydrogen is 1. Now the next element is helium. How many electrons are in helium? 2. So we have helium to be 2. And the first shell, as we already calculated, will occupy maximum of 2 electrons, which means helium can still attain its 2 electron, and that is 2. The valence electron of helium is 2. Good. Let's see carbon. I'm going to be skipping lithium, beryllium, boron. So let me move to carbon. Carbon has 6 electrons. 6. As already calculated, the first shell contains 2 electrons. So any other electron remaining will fall in the second shell, and that is remaining 4. 1, 2, 3, 4. So the valence electron of carbon is going to be how much? Good. 4. The outermost shell, the number of electrons on the outermost shell is the same as the valence electron. So I am going to be skipping nitrogen, oxygen, fluorine. I want to move to neon. What's the valence electron of neon? Neon has 10 electrons right in its atom, neon. The first shell, as we already calculated, contains 2 electrons. And the next shell, the maximum number of electrons it can occupy is 8. Remember, neon has 10 electrons and we don't want to go beyond that 10. 2 already, remaining 8. 1, 2, 3, 4, 5, 6, 7, 8. A total of 10 electrons for neon. And the valence electron of neon is going to be 8. Let me skip sodium. magnesium. Let's see aluminium. Aluminium has 13 electrons. 13 electrons. The first shell occupies 2 electrons. The second shell occupies 8 electrons. And the next shell would occupy about 18 electrons. However, if we put 18 electrons in the next shell, it makes it meaningless, since we know aluminum has 13 electrons. So the next shell would occupy the remaining electron. 10, 2 here, 8 here, making 10, remaining 3 electrons. So the valence electron of aluminium, which is the outermost shell, which contains 3 electrons. The next is, I will be skipping silicon, phosphorus, sulfur, chlorine, argon. I want to move on to potassium. Potassium has 19 electrons. And the first shell contains 2 electrons. Second shell contains 8 electrons as we calculated, which gives a total of 10 electrons. The next shell, which is the third shell, occupies maximum of 18 electrons. However, if I am to put 18 electrons in the third shell, it makes it meaningless, since we know potassium has 19 electrons. So we have 8 electrons on the next shell. So we have 2 followed by 8, that's a total of 10, plus another 8, that's a total of 18. And the next shell, we occupy the last 1 electron, and this indicates that the valence electron of potassium is 1. The same process applies to calcium, where the valence electron of calcium is going to be 2. And in conclusion, we have seen that valence electron is the number of electrons in the outermost shell of an element. We already have seen the number of electrons that each shell can occupy. The first shell, which is the K shell, can occupy maximum number of electrons of 2. The L shell can occupy maximum electron of 8. M shell will occupy maximum electron of 18. N shell will occupy maximum number of electron, which is going to be figured out. Our next discussion is on valency of elements and radicals. While we already said that valence electron is the number of electrons in the outermost shell, valency of elements is totally a different thing. Valency is the combining power of an element. It can also be referred as the number of hydrogen atoms such elements can combine with. Let's figure out. We can find out the valency of elements using the shell configuration, and let's see that out. Valency and valence electron are always interwoven, so we need to understand the difference between the two. Let's see the valence electron configuration using the shell process for all these 20 elements. For hydrogen, the valence electron is 1. For helium, the valence electron is 2. For lithium, the valence electron is 1. However, let's see the configuration to figure out the valence electron. 2, 1. So the valence electron is 1. For beryllium, 2, 2. The valence electron is 2. For boron, 2, 3. The valence electron is 3. Carbon, 2, 4. Valence electron is 4. Nitrogen, 2, 5. Valence electron is 5. Oxygen, 2, 6. Fluorine, 2, 7. Neon, 2, 8. Sodium 2, 8, 1. And the valence electron is 1. Magnesium 2, 8, 2. Aluminium 2, 8, 3. Silicon 2, 8, 4. Phosphorus 2, 8, 5. Sulfur 2, 8, 6. Chlorine 2, 8, 7. Argon 2, 8, 8. Potassium 2, 8, 1. Potassium 2, potassium 2, 8, 8, 1. And the valence electron of potassium is 1. Calcium 2, 8, 8, 2. Now, this valence electron gives us an indication of what the valency of the element will be. How do we figure out the valency of elements? We have two cases to determine the valency. Case 1. All elements whose valency are from 1 to 4 remains the same, meaning their valency remains just 1 up to 4. So, the valency of lithium is 1, meaning that only one hydrogen can combine with lithium. The valency of beryllium is 2, meaning 2 hydrogen can combine with beryllium. So the valency is the number of hydrogen that can combine with the given element. So all numbers from 1 to 4 are having the same valency. Let's see, for the case of nitrogen, number from 5 to 7 are in case 2. And to get their valency, we subtract it from 8. So let's figure out the valency of nitrogen is going to be 3. The valence electron is 5, so we need to subtract from 8, and that is 3. The valency of nitrogen is 3. What about oxygen? Oxygen has valence electron of 6, and that falls in case 2. So we minus, and that is 2. So the valency of oxygen is 2. Fluorine, 7 valence electron, which is in case 2. And we need to subtract that from 8. 8 minus 7, that's 1. So the valency of fluorine is 1. Then has valence electron of 8, and 8 minus 8 is 0. When we have 0 that way, it shows that there is no valency for such element. And in general, such element is known as a noble gas. So neon is an exception of this. We have sodium 1, and the valency of sodium is 1, still in case 1. So it falls in case 1, and the valency is 1. Now let's see the valency of chlorine. What will that be? Guess. 7. 7 valence electron, and the valency would be what? 8 minus 7, which is 1. So the valency of chlorine is 1. What about argon? What about the valency? The number of electron, which is the valence electron, is 8. 8 minus 8, 0. So which means that it's a family of the noble gases. We are going to see in the next class what we have next and how we can use the valency to form compounds. In the previous class, we talked about the valence electron and the valency of elements. Now, we are going to be talking about forming compounds using valency. To serve as a recap, let us figure out the valency of the first 20 elements. So, the valency of hydrogen is 1. All number whose valence electron falls from 1 to 3 remain and retain their valency. If it goes from 4 to 7, we subtract it from 8, and the remaining answer we have is the valency. If we subtract it from 8 and we have 0, then such element does not have any valency, and they are usually called noble gases. Helium is a noble gas because the only electron it has is 2, which is the outermost electron. We say it is exhibiting the duplet configuration, so it does not have any valency. The valency of lithium is 1, beryllium 2, boron 3, carbon 4. Nitrogen falls in case 2, as we already said in the previous class. So we want to say 8 minus 5, and that is 3. The valency of nitrogen is 3. For oxygen, 8 minus 6, 2. The valency is 2. Fluorine is 1. This is neon. It does not have valency. Sodium, 1. Magnesium, 2. Aluminium, 3. Silicon, 4. Phosphorus, 8 minus 5, 3. Sulfur, 8 minus 6, 2. For chlorine is 1. Argon does not have valency, so it's a noble gas. Potassium is 1, and calcium is 2. This alone will help us to form any compound with their right formula. So what is a compound? A compound is a substance that contains 2 or more elements that are chemically combined together and cannot be split by ordinary chemical process. You must have seen something like this before. H2O. That is what we mean by compound. How can we form compound? By their valency. This is very cheap and easy. We have hydrogen and oxygen. So we need to figure out the valency of hydrogen is 1. And the valency of oxygen is, let's check, 2. When the valency of the element is given, we cross multiply. So what we have now is H2O1. To avoid repetition, we can see that we have just 1 oxygen. So we remove the 1 that is beneath, and this is a balanced compound for water. So in general, when we are given any element and its valency, say for example the element and the valency. If the element is A and the other element is B, given the valency of A to be M and the valency of B to be N, then the compound formula would be cross multiply and write ANBN. We should be careful and put this into consideration that the valency is usually written as a subscript. So when you are writing a compound, take for example water, you write H2O this way, then you would be wrong because the number for the valency is written as a subscript, just as you can see right here. So we are going to be seeing more examples on how to use valency to make the formula of a given compound. We can determine the valency of radicals just like we determine the valency of elements. What do we mean by radicals? Radicals are 2 or more elements with either positive charge or a negative charge. They are usually known as ions. And we have ammonium ion, and the valency is 1. So the number of charges is directly proportional to the number of valency of such radical. We have just plus on NH4, just plus, 1 plus, so it can be 1 plus or plus 1. So the valency is 1. Similarly to trioxonitrate 5, the valency of trioxonitrate 5 is always 1. The valency of hydroxide is 1. However, for triazocarbonate 4, the valency is 2 minus, we have the 2 minus, so the valency is 2. For tetraososulfate 6, the valency is 2 as well, as we can see, as the ions indicate. Tetraosophosphate 5, the valency is 3. PO4 3 minus, so the valency is 3. We can determine the compound if we are given radicals and its valency. So let's take, for example, we have radical or elements, then valency. So take, for example, we have this element K, and let's check back. K is potassium, and our potassium right here is 1. The valency is 1. And given this trioxonitrate 5, NO3 minus, so the valency of that is 1. Generally, when we are making compound using radical, we do not need the charge. So let's cross multiply. This goes to meet this. And the formula here is going to be K1 and NO3 1. Since we are having 1, to avoid repetition, we can just remove the 1, and the 1 here can be removed as well. So there is no subscript affecting the bracket. We can rewrite this as KNO3. And this can be read as potassium, 3 means trioxonitrate 5. So we know NO3 is talking about trioxonitrate. So this is potassium trioxonitrate 5. Let's see one more example. Radical or element. Example 2. The valency. So let's say we are having element hydrogen and radical SO4, 2 minus. The valency of hydrogen is 1, and the valency of tetraosophosphate 6 is 2. As we already mentioned, we do not need the charge when we are making the cross multiplication. So looking at this, what do we have? We have H2 and SO4 base 1. We can see that this entity is just written one time. So we can decide to remove the 1, and the formula gives us H2SO4. And how do we call this? We know that SO4 is ososulfate 6. So we have 2 hydrogen, that is dihydrogen tetraososulfate 6. So the name is dihydrogen tetraososulfate 6. And the 6 is always in Roman numeral, just like you can see in the previous ones given here. Thank you.